Log on, tune in, find out. Another good idea from Cambridge.
Codes, the implications of using separable covariance functions.
Okay, thank you, Tony. Can everyone hear me okay? So this is a talk in two parts. There's a theory part and there's an application part. I'll get straight to the application part so you know where we're going. Whenever we're emulating a complex computer code, if we're following a statistical route, then typically we end up proposing a prior of some kind for that code, which we then condition upon runs of the code, what we would call the ensemble of runs of the code. And in order to do that in a probabilistic way, either in terms of a second order update or typically in terms of a Gaussian process update, we need to construct a covariance function over the p-dimensional parameter space or input space of the code. Okay? Now, constructing p-dimensional covariance functions is very hard, of course, because covariance functions have a very precise structure. They have to be symmetric and non-negative definite. And so what we usually do in this case is we take advantage of the very tractable fact that you can make a p-dimensional covariance function by taking the product of p one-dimensional covariance functions. Okay? That's a very useful thing to do. Sometimes that's the whole of our emulator, and sometimes that's just an important part of our emulator, but in almost all cases we find that that's what we do in practice. Okay? We use separability either in the emulator itself or in the emulator residual. Now, that's not just very convenient from the point of view of computation. It has this lovely property, for example, that you get a characteristic length scale for each component of the covariance function, which is a very easy thing to learn about. It's also useful because you can use those length scales as the basis of a screening exercise, which can be very useful in practice when you're not quite sure about which inputs are important and which inputs aren't. And then in a field that I work in a lot, if you're emulating a multivariate output, then it's very convenient to have this product structure in the covariance, because then you effectively have a grid of data. You know, you have, if you like, one row for each run of your code and one column for each component of the code output. And if you have a covariance function which is separable, then the variance matrix of that object, effectively a variance tensor, because the object is two-dimensional, so the variance is four-dimensional, has a Kronecker product structure. And when you need to invert that variance matrix to do the conditioning, the inversion is not an order n times p cubed operation, it's an order n cubed plus an order p cubed operation, so it's much, much quicker. So that's why we do it in practice, and those are compelling reasons in large problems. I don't think there's any doubt about that at all. But what we would like to know, just to be absolutely sure, is that in adopting this framework, we haven't painted ourselves into a corner by making very strong judgments about the underlying process that we would find hard to defend. Okay? That's what we want to be sure about. And this talk is really about what it means to make judgments of separability in covariance structures. And I think I'll just start with the message itself, just so we know where we're heading. So this is the message. And the message is this: if our function f, say, that's our stochastic process, we'll give it two inputs, x and y, but the argument is fully general, right, has a separable covariance structure, covariance function, then, and now this is slightly hand-wavy, but there is precision behind what I'm writing here, but I don't want to go into all the details. It is effectively equivalent, so that's not quite equivalent, there's a little wiggle there, right, to the product of a process in x and a process in y, and these two processes are effectively uncorrelated. Okay, so that is the message, and it's a very strong one, because this is saying that if you adopt a separable covariance structure in your emulator, you are asserting there are no interactions between the inputs x and y. Okay, that's a prior assertion. Now, if there's one thing that we're absolutely sure about, is if someone asks us to emulate a complex computer code, right, almost certainly there are interactions. The reason we build these codes is to try and find out what those interactions are. Okay? So a starting point which says there are no interactions in my code seems like an indefensible starting point for an emulation. Right? And this is what we want to get to the bottom of.
So chanting Well, that's the product of two functions, where often in, say, an analysis of variance, we might cheat and say an interaction term is actually the product of x and y.
Mm-hmm.
In that sense, are those sorts of interactions part of your prior then?
Now, I'm only looking at this very particular case here, right, where effectively this function, this joint function is going to look the same along y no matter where you stand in x. And it's going to look the same in x no matter where you stand in y.
And will not, say, large values of y and large values of x together give you an interaction sort of effect in the output in the product for the response that you're emulating?
No more than you get in the simple product structure here. Okay. Yeah, I mean, this would be called no correlation in spatial modeling, for example, because under this structure, the correlation structure in x is the same for all values of y, and the correlation structure in y is the same for all values of x. Okay? So I think of it as no interactions, basically. So we want to get to the bottom of this, and we want to find out what its implications are for emulation. Now, this is a theoretical result which I've been working on for about a year. I'm not going to give you the theory, but I will state the key properties under which this becomes true. I'll explain why we get to this situation here, and then in the last part of my talk, I'll just say why, in fact, this is not a disaster for emulation as we know it. In fact, there's some very reassuring findings about emulation that says mostly our emulators don't have this form, and the ones that do is probably not a disaster anyhow. Okay, so that's the good news up front. Right? Okay, so that's the message. Now, a little bit of background so you know exactly the basis for this result. It's a very general result, but this then is the setup. Our function f is just going to take two inputs just for simplicity and map into a real value quantity r, so this is a scalar output. And the restrictions that I require, and these are completely standard in computer experiments, are first of all that xy lives in a product space, which we'll write as curly x times curly y, right? And that curly x and curly y are both closed, bounded intervals of R. Okay, so this parameter space is a box, right? And when we generalize to an arbitrary p, finite p, number of inputs or parameters, then all the generalizations go through immediately as long as you have a box structure for your input space. Okay, so I think old school we would say that x and y are variation independent. Okay? And then we also require that, and we'll come down here for this one. Whoops, there we go. That the covariance function for f is continuous. So we require that the covariance of f at x and y and f at x prime and y prime, which we'll write as kappa xy x prime y prime, right, is continuous. And actually it has to be continuous on its domain, of course, and that implies, because the domain is closed and bounded, that it is bounded above. Okay, so it's bounded above. So we are dealing with processes that have finite second moments. And then without loss of generality, we're also going to just take the mean off. Okay. Going to subtract the mean function just so we can not worry about it. So that's without loss of generality. Clearly the mean exists if the variance exists, so that's totally doable. So those are the only conditions that I'm imposing upon us right now. This is a stochastic process of arbitrary distribution, subject only to the fact that it has finite second moment. Okay, there's nothing particularly Gaussian about this, and that will be important later on. So that's the setup, and now if I tell you that f has a separable covariance function, what I mean is that kappa of x, y, x prime y prime, right, separates into the product of two univariate covariance functions, so that then becomes kappa, and it has x prime kappa y prime. Okay, so that's what we mean when we say that it has a separable covariance function. Right. So now there are two results basically. There's the hard result and the easy result. The hard result I'm just going to state, and this is basically a representation theorem. It says if f has a separable covariance function, then it must be of this form, right? Or rather, it is equivalent to an expression in this form. So we'll write that over here. Representation. So the representation says that if f has a separable covariance function, then there exist sets of functions gi and h of j, okay, such that f can be written as the limit of the product of sums 1 to n over zij, those are random quantities, and that's gi of x and hj of y, where zij are mean 0, variance 1, and uncorrelated. Okay, now that is a representation theorem, so I'm going to strengthen what I've said there. So this is an implication, but the strength of the result is f has a separable covariance function if and only if. Okay, so that's the strong result. Now, that's how we're going to get there, yes. Let me just say that this result, if curly x and curly y were finite, right, and f was Gaussian, this result would be pretty straightforward. Okay? The trick comes from proving it in the completely general case for any stochastic process with finite variance and over a continuum in the input space. Now, the construction to go from here to here, separable covariance function, that's pretty straightforward. We need to tighten up the definitions a bit. We need, of course, that these are continuous, and we need that this convergence here is uniform. That's not too bad, actually. Going from this to this is totally doable. The interesting result is going the other way around, starting with a separable covariance function and then proving that there is a decomposition of this structure. And exactly as Hugo says, you use Mercer's theorem on each component of the covariance, and then you use the Calhoun-Loewe expansion, right? And you end up in something that looks a bit like this. And the trick basically is to make sure that all your convergences are right. So you need strong and uniform convergence appropriately. And then you can find that there's a direct equivalence between these two statements. The statement that f has a separable covariance function and that this decomposition exists. Okay? So that is a representation result. It goes both ways. Now the interesting thing is to take the next step and ask ourselves under what conditions we can actually think of f as a product of two uncorrelated processes, and that's where I want to get to. Now in fact, it's actually quite easy to make that step. If we take this representation here, then we can create a new stochastic process, which we'll call f prime, by taking out these zij's. So zij is a collection of zero mean variance 1 uncorrelated quantities, and replacing them by product zi Zj prime. So let's replace the set Zij with the set of products we'll just write Zj prime. Okay. Now, if we don't want to change the mean and variance structure of F, then we have to be sure that Zj prime has the same mean as Zij, and Zj prime and Zi prime Zj prime prime has the same covariance structure as Zij, Zi prime J prime. Okay, so we just need, in fact, that the expectation of Zi Zj prime is equal to 0, and that the covariance between Zi Zj prime Zj prime prime. We'll just do this with delta functions. Okay, that's what we require. Okay, now if we do that, we haven't changed the mean or the variance of the process, but it's clearly a different process. It's a different process, right? We've taken one set of random quantities, these Zij's, which have a complex joint distribution, right? We don't know what it is, but they have a complex joint distribution, and we've just replaced them with another set, right? Different distribution, same mean and variance, different distribution. But the fact is that they do have the same mean and variance, and consequently, if we drop Zi Zj prime up into there, right, we'll end up with an expression that factorizes into components in I and components in J. Okay, so in fact, in this case, we'll construct a new process, F prime, now it's going to factorize into terms in I and terms in J. Right, and this is, we'll call that f of x, and we'll call that f of y. And because Zi, this family of Zi's, are uncorrelated with the family of Zij's, right, this thing here is uncorrelated with this thing here. Okay? But f prime has the same mean and variance as f, right? But it doesn't have the same distribution, but it is separable into the product of uncorrelated processes, one in x and one in y. Okay? So in other words, we can go straight from the representation theorem, right, to the construction of a new process, f prime, which has the same mean, the same variance, right, different distributional characteristics apart from that, of course, yeah, but is in fact the product of two uncorrelated processes. Yeah? So, to put that in words, right, when I wrote equivalent with a wiggle at the top here, what I mean is second order equivalent, right? My f of x and y is second order equivalent to the product of uncorrelated processes. So if you only care about means and variances, it's the same process. Yeah? And the reason that's important, of course, is if we were to update a Gaussian process with the ensemble of runs of our simulator, that would be a second order update. Okay, so this is directly relevant to Gaussian process emulators. So, I think that's a pretty interesting result. Now, let's talk about emulation. When we do emulation, we typically write down a prior for our process, our simulator, our complex code, and it usually has the form of f of x and y, and then we have a collection of regression terms with uncertain coefficients, and then we have a residual term, right, where this residual term is always treated as having a separable covariance function. Yep. And sometimes, of course, this is entirely suppressed, and sometimes you just have a constant. Right? But always somewhere in your emulator, you're likely to find, right, that there is a residual term with a separable covariance structure. I've built one emulator that doesn't have a separable covariance structure, which was based upon strong information from the modelers. In fact, it was the TiGCM emulator that Steve just mentioned. But typically they do have separable covariances. Now the question is, okay, the residual has a separable covariance function. Does the process f have a separable covariance function? And the answer, happily, is no, as long as these betas have positive variances. Okay? Because if you just compare this expression here with the representation theorem, you can see that you can't get from one to the other, right, if the betas have positive variances. Right? You cannot reorganize this expression here, even if the g factorizes into g of x, h of y. Right? You cannot get back up to there. Okay? So, strong conclusion 1, if you've got regression terms and the coefficients on those terms have positive variances, right, your emulator, your prior emulator, does not have a separable variance. Good news, okay, good news. But there is a catch. The catch would be if you thought, and I think maybe this is what Steve has just done, if you thought that you would pull a fast one, right, estimate these betas, and then plug in their MLEs and forget that they're uncertain. Steve? Yep. Now you have a separable covariance function. Now your function is behaving like the product of uncorrelated processes. It's no interactions. Okay? But as long as you preserve some uncertainty in the betas, right, then you don't have a separable structure. But you can see that if it is the case that the variance in your emulator is dominated by this term here, even stuffing some uncertain betas in is going to make your emulator nearly separable. Okay? So you want to be careful about near separability. Now the question is, if you start off with a separable prior, what happens when you update your prior with the ensemble of runs of your code? Right? Is, for example, separability like stationarity, is it something that we assume in the prior because we know that as soon as we condition or update, it's going to disappear? Right? And the answer, happily, is yes. Okay? The moment you condition on even one run, right, the separability that may or may not exist in your prior is erased. And we can see that it's erased by, again, looking at the representation theorem. The moment you condition on a run, you plug in an explicit value here. Right? Now, what that means is that you induce a covariance across the zij's. They're no longer uncorrelated. Yeah? So conditioning on one run will do it. Even if you started with a separable prior for your emulator, the moment you update, you lose separability. So in that sense, it's just like stationarity. Yep? It may be something that you choose to do at the start of the process just to get up and running, in the knowledge that once you condition or adjust, you're off the hook. Yep? And your emulator will no longer be behaving like the product of uncorrelated processes. In other words, it'll have interactions. Okay? Now, there's one caveat, of course, and this is in a situation where you're working in large experiments, as I tend to do. So if you're working in a large experiment, the code is really expensive to run. And if you sit down with the people who built the code, maybe it's a climate simulator, they can list probably 100 parameters or inputs that are uncertain and that they would like to vary in their experiment. But of course, you can only afford to do about 100 runs, so that's ridiculous. Right? But you might beat them down to about 30. Okay? So then you're doing an experiment where you're varying 30 parameters and you only have about 100 runs. It's a bit of a disaster, really, but you do what you can. Okay? You try and get the best experiment that you can. But you know perfectly well that the runs that you've got, right, are in no sense spanning the input space that you're trying to model. Right? In particular, if you try to drop 100 points into even a 10-dimensional space, what you'd find is that the volume of the convex hull of those points in the parameter space would be a vanishingly small fraction of the volume of the whole parameter space. Okay? Now, why is that a problem? Well, suppose that you want to treat your parameters or your inputs as uncertain, and you want to integrate them out to look at a sensitivity or an uncertainty analysis. Well, separability is going to behave like stationarity. Once you condition upon your ensemble, inside the convex hull, right, the process will not be behaving like a separable process because it has lots of interesting interactions and so on. But as you drift away from the convex hull into the corners of your design space, your process will be returning to its prior structure. Right? That's what processes do when you move further and further away from the runs. Okay? So if you've done a run, an experiment where the parameter space is large and you haven't spanned it with the runs in your ensemble, then actually most of the volume, even after conditioning, is going to look like the prior process and not like the conditioned process. And so in that case, when you integrate out the parameters, it's going to look like a process with a separable covariance structure. It's going to look like, effectively, the product of uncorrelated one-dimensional processes. Okay? Now, the way that you can definitely avoid that, again, is by including regression terms. Right? If these guys are doing all the work, you've got nothing to worry about. Right? Because they're going to carry non-separability into the corners of your parameter space. Yeah? The moment you condition on these, it's fine. But I think the cautionary thing that I've learned from thinking about this problem is that although I felt intuitively that it was always good to have regression terms in my emulator, I feel now, especially for very large problems, that regression terms are absolutely crucial in my emulator, and that it's important that I remember that even after conditioning, these regression terms, these beta i's, retain some variance, okay? So that they're genuinely, if you like, erasing the separability in the prior, right, through the conditioning process. Okay? So that's the message of my talk. There was a little bit of a theory component, but really I think I've come to this from the point of view of what works and what doesn't work for emulation, and are we in fact painting ourselves into a corner by making a decision on the basis of tractability that traps us into an unrealistic representation of the function that we're modeling, in particular the absence of any possible interactions between the inputs. And I think my conclusion from this is that although it looks bad on the surface, actually when you look under the lid, as long as you follow the practice of including reasonable regression terms in your emulator, then you haven't actually compromised the analysis that you intend to make if you're involved, for example, in integrating over the input space. Okay? Thank you.
Any questions? Yes.
Yeah, one question. How can you replace the, say, n square random variables with the 2n random variables and say that they are uncorrelated?
So the replacement here.
But there are only 2n random variables, right? On the left-hand side, you have n squared of them. So, but the n squared are uncorrelated.
Yes.
Yeah, so how can you reduce the dimension and still claim that they are uncorrelated?
So what we require is that if we just imagine that that this was previously Zij, and this was previously Zi prime j prime, right? Then the requirement is that Zij and Zi prime j prime are uncorrelated if either I is not equal to I prime or j is not equal to j prime. That's the condition up here. Okay? So in order for that to be true, right, it is sufficient if we take two uncorrelated families of random variables and then take their product.
But the point I think it would be that whilst it's possible for you to create n squared uncorrelated variables, there are dependencies in this system which are not captured but just the second order.
Yes. Oh yes. No, but it's all second order. That's right. The thing I must stress, when you make this substitution, you have completely mucked up the process. Right? It's not the same process at all. So all the higher order structure, right, is not being replicated in these product terms. It's all been lost. Yep. If this f here was a Gaussian process, right, then it would follow that these z's are Gaussian random variables. They are independent, standardized Gaussian random variables. Right? That would be the case. And if that was the case, and the convergence would be much stronger in that case, if that was the case, then replacing Zij with the product Zi, Zj, these would not be Gaussian. They would be something else entirely. Yeah? And they would have different higher moments, and different skewness, different kurtosis, all sorts of things. And then, when you take this product here, this will not be Gaussian. Right? This will not be Gaussian. This product will not be Gaussian. This will not be Gaussian. It's a totally different process. It just happens to have the same mean and variance structure. Yeah? So the equivalent is only to second order. Okay.
Question? Yeah. Okay. We know that a tensor product of reproducing cantilevered spaces is a reproducing cantilevered space with a separable covariance. And your construction reminds me of the construction of tensor products.
That's right.
Did you consider proving that using RKHS?
I think actually it's a very similar result because they both depend upon Mercer's theorem. Yeah, I mean that's the fundamental theorem in reproducing kernel Hilbert spaces, and it's the same construction. Yeah.
Because I mean, the proof, the functional analysis proof would be direct.
Yeah, actually, it's only a few lines in each direction. It's not horrible. The trick is, of course, to get convergence right. So you've got to use, tedious results like if two things are converging absolutely or uniformly and they're continuous, then the product is converging. It's the boring stuff that you have to get right.
So one more quick question, if there is one. Dave.
So Jonty, this is probably like the fact that we have a different word for a billion in our two languages, right? So it's probably like this. All right, separability means no interaction, the way you say it, right? But the way I'm thinking of interaction, for instance, an ANOVA, two-way ANOVA model with full interaction, that would be something you could write in that product form, right? And it would have sort of the usual thing that, if y is high and x is high, it's different than if y is high and x is low, that sort of thing. Now, I'm suspecting you're talking about some other kind of interaction or something else than just sort of this ANOVA-like interaction thought that I have from America.
Yeah.
Take logs, Dave. Take logs.
So I think, yes. Well, actually, it does come down to that, because I think that your ANOVA type structure is pretty like an additive variance decomposition, isn't it? Well, this is a different kind of approach. When I say separable, I mean very, very precisely a separable covariance structure. And when I say no interactions, I simply mean that no matter where you stand on the x-axis, as you look along y, right, it will look the same. And that's what this product structure is actually saying. As you look along, your height will be different because it will depend on where you are in x, but as you look along y, it'll have the same shape.
But if you happen to be on x where that function's 0, it'll look flat, won't it?
Yes.
And when you go to some place where x is where f is 1, you'll see something that goes along with your y function.
That's right. The scale will change. Yeah, the scale will change with x, which is why it's often expressed in terms of correlations, because the correlation takes the scale factor out, and the correlation structure is identical no matter where you are in x. But when I say look the same, I mean the hills all have the same shape and so on. Yeah.
We're going to have to stop there, I think. Thank you very much, John.